Hello students. So as you can see, today the topic is rectifiers and rectification. So what does rectification mean? Well, rectification is a process of AC to DC conversion. AC stands for alternating current and DC stands for direct current. So it's a very simple process of alternating current to direct current conversion. So which is the usual device that helps in the rectification process? The answer is it's a two-terminal diode. So a diode always acts as a rectifier circuit. Now we also say that rectification is a process wherein the current flow is allowed in a diode in only single direction, whereas in the other direction or in the opposite direction the flow of current is blocked by the diode. So how does that happen? Well, we will try to understand the working of a rectifier circuit. Okay, so to start with, how many types of rectifier circuits are there? Well, the first and the foremost simplest type of rectifier is a half wave rectifier circuit. Half wave rectifier circuit. So a half wave rectifier circuit uses only one diode, and it performs rectification for only half of the cycle or half of the input cycle. In the other half, rectification will not happen. The other type of rectifier is called a full wave rectifier. So a full wave rectifier uses either 2 or 4 diodes. So if 2 diodes are being used, we call it as center tapped full wave rectifier. Center tapped full wave rectifier. If we use 4 diodes, then it is called a bridge rectifier. Bridge rectifier. Well, both center tapped and bridge rectifier are full wave rectifiers itself, which means they perform rectification for both the input half cycles, which means rectification happens in both positive as well as negative cycles of the input signal. In short, usually we denote half wave rectifier as HWR, which means half wave rectifier, and a full wave rectifier is usually denoted as FWR. So full wave rectifier. Alright, so let us try to understand the working of a full wave rectifier circuit and how does the rectification happen in the case of a half wave rectifier circuit. Okay, so let's try to understand the half wave rectifier. So how does the circuit of a half wave rectifier look like? So as I had already mentioned, a half wave rectifier circuit uses only one diode. So this is one diode which is being used. So let's apply a sinusoidal input signal for this half wave rectifier. Let me just draw the input waveform. Let's assume that this is a sinusoidal input signal which continuously varies with respect to time. Let the peak values be plus Vm and minus Vm. Let us denote this as Vi, small vi. Okay, since it is a sinusoidal signal, it can be defined as Vi is equal to Vm sine omega of t, where omega is the angular frequency and Vm is the peak voltage in the positive as well as negative half cycle. So when we apply this particular input signal to this diode, what will be the output? Now the output is always across a load resistor. So let RL be the load resistor across which the output is to be seen. So during the positive half cycle, input Vi, and what will be the output across the load resistor RL. Okay, so during the positive half cycle, which means we are applying a positive voltage to the anode and in turn a negative voltage to the cathode. So which makes sure that the diode is forward biased. Now by the way, we are assuming that the diode is ideal. In this case, let's assume that the diode is ideal. That means as soon as we apply a input signal, the diode instantaneously starts conducting. So when it instantaneously starts conducting, how does it behave? Well, it behaves as if it is a short circuit equivalent. Okay, so this is the short circuit equivalent of the diode when it is forward biased. So let me just write it as FB stands for forward biased. So under the forward biased situation, the diode behaves as if it is a short circuit equivalent. Okay, so we know that for a short circuit, the current flows instantaneously and the entire voltage appears across load resistor RL. Because we have assumed that the diode is ideal, when it is conducting, virtually there is no voltage drop and the entire input signal or the input voltage appears across the load resistor RL, right? So if I just want to draw the input signal as well as the output signal in a common graph with respect to common scales, this is how it looks like. Well, if this is the input signal, I am drawing the same input signal. So if this is the input signal, right? So during the positive half of the input signal, as I had mentioned, the diode behaves like a short circuit. So current flows through the diode and the entire voltage appears across the load resistance RL, due to which at the output side I will be getting the exact replica of the input signal. That means if the maximum peak voltage is plus Vm, at the output side also I will be getting plus Vm. Okay, so this happens during the forward biased situation. Now during the negative half, okay, so during the negative half of the input cycle, so when I say negative half, that means I am applying a negative voltage to the anode of the diode and positive voltage to the cathode of the diode. So what will be the situation of the diode now in this case? Well, during the negative cycle, the diode will be reverse biased. RB stands for reverse biased. So that means the diode will not be on. It behaves as if it is a open circuit. So we know that whenever there is an open circuit, no current flows. Okay, which means the diode current will be 0. Whereas in this case, diode current flows. Okay, in the previous case, the diode current flows. Whereas in the negative half of the input cycle, the entire input voltage drops across a open circuit and there is no diode current, so no voltage appears across the load resistance RL, which means during the negative half cycle we do not get any voltage appearing across the load resistance RL. Okay, so this is how a half wave rectifier circuit works, which uses a single diode, right? Okay, well, conceptually this is very simple. There should not be any confusion regarding this. Okay, well, this is the ground which I had forgotten to mention. Okay, fine. Now, since we have understood the working of a half wave rectifier circuit, now what are the important parameters that are associated with respect to the half wave rectifier circuit? I will be only listing the important parameter values. Okay, fine. The first and the foremost important parameter for a half wave rectifier circuit is the average DC voltage or the average DC current. Okay, so let me just write important parameters in half wave rectification. Okay, so the first important parameter is VDC. Okay, so what is the value of VDC? It is Vm upon pi, where Vm is the maximum peak voltage. Okay, now basically what do we mean by DC voltage? Well, it is the average voltage that is appearing. So if I just take the average voltage of both the positive as well as the negative at the output side roughly, okay, so this is the average DC level voltage, which I can mention it as VDC. Okay, well, mathematically it can be derived that VDC will be equal to Vm upon pi. Similarly, the second important parameter is VRMS. Well, VRMS for a half wave rectifier circuit is mentioned as Vm upon 2. Okay, right. What is RMS? RMS stands for root mean square value. Okay, the details of how do we obtain at these particular expressions is mentioned in one of my videos. The description is given. You can just go through it in the description section of the video. Similarly, so the third important parameter is efficiency. So efficiency of a half wave rectifier circuit, again when derived, comes to around 40.6%. Okay, what does that mean? That means the efficiency of a half wave rectifier is not that great, considering the input and considering the output. Well, the AC to DC conversion is not that great in the case of a half wave rectifier circuit. It is just 40.6. This is exactly one of the reasons why we rarely use half wave rectifier circuits nowadays, except for one or two particular applications. We rarely use half wave rectifiers. Okay, so instead of half wave rectifiers, we usually go for full wave rectifier circuits, which has got a much better efficiency when compared to a half wave rectifier circuit. Okay, so the fourth important parameter is the ripple factor. Okay, so the ripple factor for a half wave rectifier is again 1.21. What does it mean? It means there are too many ripples in the case of a half wave rectifier circuit. Okay, fine. Next, the last important parameter is peak inverse voltage, which is PIV. The peak inverse voltage of a half wave rectifier is mentioned as Vm. Okay. Now, we usually call this type of a circuit as a half wave rectifier circuit without a filter. Okay. Now the question comes, what is a filter? Okay. See, the output waveform shows that it's not a pure AC to DC conversion. There are sufficient amount of ripples present at the output side. Okay. Well, can we reduce these ripples? Yes, they can be reduced, and the solution is to use a filter circuit. So whenever we say a filter, it means we'll have to use a capacitor in parallel to the resistor. Well, so a half wave rectifier has got too many ripples. Okay, well, we had seen that the ripple factor of a half wave rectifier is 1.21. So is there any way to reduce the ripples? Yes, the solution is use a filter. So when we say filter, which is the component that can be used? Well, it is nothing but a capacitor. Okay, so if we use a capacitor in parallel with respect to the load resistor, this particular circuit acts as a better half wave rectifier. Well, what do we mean by a better half wave rectifier? It's nothing but the ripple contents are being reduced. Okay, so how will that be reflected with respect to the output waveform? Okay, well, this is the output of a half wave rectifier without filter. With filter, how does the output look like? Okay, so initially during the positive half cycle, the diode conducts. Okay, the diode conducts and the capacitor gets charged to the maximum peak value of the input voltage, which is Vm. Okay, so initially this is how the output looks like. Okay, so after that the voltage at the anode as well as the cathode will be equal. Okay, which means the voltage appearing between these two terminals will be the same, due to which the diode will be reverse biased. When it is reverse biased, the capacitor charge starts discharging in this direction. Okay, so this particular discharging phenomena is being reflected like this. Okay, so again when the discharging happens, again the diode gets forward biased and then the capacitor gets charged. So this particular phenomena, it keeps on repeating, due to which we will be getting such type of a waveform. Now the solution is, what is the difference between this waveform and this waveform? Well, it can be very clearly observed that with filter the ripple content has been reduced to a great extent. Now, can it be reduced still further? Yes. As we go on increasing the value of the capacitor, the ripple contents go on reducing. So, if I just go on increasing the value of the capacitance, I will be getting a better DC. Okay, well, I cannot say that it's a pure DC. It is still a pulsating DC. However, the ripple contents are being reduced greatly. Okay, but still, as I had already mentioned, a half wave rectifier is not that efficient, we will have to go for a full wave rectifier circuit. One more point to be observed here is the time constant RC should be large enough such that or so that the discharging time of the capacitor has to be considered here, which means RC should be large enough than the discharging time of the capacitor. Okay, only then we can understand the concept in a better way. Okay, well, I think you have understood the concept of a half wave rectifier circuit with filter and also without filter. Okay, yes, okay, so thank you students.